as we look at 3D shapes, we're going to start seeing what we can do with those 3D shapes. Now think back to dilations. Here I have a rectangle with length L and width W, and I blew it up to be twice as big. In other words, I doubled the length and I doubled the width. You can observe how does that affect the area and the perimeter of the shape. Take a guess. How many of these original rectangles would fit in the new bigger rectangle? If you guessed 4, you're correct. You can see down here we did a little bit of math. Twice the length times twice the width makes 4 times the length of times the width. The perimeter is a little bit different though. Let's look at the math. So here, our area became 4 times larger. Because we doubled the length and we doubled the width, those doublings multiplied each other to create an effect of 4 on the area. But our perimeter is just doubling the length. And so if I make it twice as long, it actually is only stretching it to be exactly double. So the perimeter is 2 times larger when we double the shape, and the area became 4 times larger. What happens when we start looking at 3-dimensional shapes? So here I have a rectangular prism, and then I have the doubled version of the same rectangular prism. You can see the length, 4 centimeters, it becomes 8 centimeters, 3 centimeters becomes 6 centimeters, and 2 becomes 4. So what we're going to do is we're going to compare the volume. And we're using a very simple formula, length times width times height. And you can imagine we're using rectangular prisms because they're just easier to do the math for. At the end, we get 24 centimeters cubed for the original and 192 cubic centimeters for the doubled shape. So remember, we doubled each of the dimensions. We doubled the length, we doubled the width, and we doubled the height. Now, that's way more than double. So if you thought that if we doubled the length, width, and height that we would get twice as big of a shape, you're actually completely and totally wrong. It's 8 times larger. 8. 8 of the original shapes would fit into the doubled shape, which is where I have to give a little disclaimer. These are not drawn to scale, as you can probably tell. But it's way more than double, which is the big point. When we double the dimensions, we get an even significantly larger shape. Now, why 8? And why 4 from before? You can even try to relate it back to the 2D shape. Well, if I double every single dimension, what I'm basically doing is I'm adding to this formula a 2 times 2 times 2, and then all of that times the original. So 2 times 2 times 2 is in effect 2 to the 3rd power. And that makes sense because we doubled each of the 3 dimensions. So doubling and doubling and doubling results in an effect of 2 to the 3rd power. Now, if I did 3 times larger for each of those, well, you'd see a 3 there. Or 4 times larger for each of those, you'd see a 4 there. What we're in effect doing is we're taking that scale factor and we're scaling it up for each of the 3 dimensions. Now, before, when we were looking at a 2-dimensional figure, a rectangle, there were only 2 dimensions. So doubling meant our overall area effect was 2 squared. So they are very much related. Now, I'm going to leave you on a bit of a cliffhanger here, just giving you a warning. I want you to think, how would the surface area be affected by this doubling? So we have the same shapes here, and I'll give you the formula if you'd like to use it. Surface area is equal to 2LW plus 2LH plus 2WH. So basically finding one of the rectangles and then doubling it just to do the matching side on the other side. And your entrance ticket for class is going to be telling me how much larger is the surface area when we doubled the shape. Is it twice as large? Is it 4 times as large? Is it 8 times as large? Or some other new figure? Let me know. And A little hint is think about the surface area units. So our final surface area is going to be measured in centimeters squared. That's my hint to you. I look forward to hearing your theories.